Hey, my name's Casey, and if you want to see me walk through more LeetCode problems, you can subscribe. So I'm gonna walk you through LeetCode 239 sliding window maximum. So what do they give us here? They give us the nums array, which is just an array of random numbers, and this k equals 3, which is just a window size of size 3. So let's just look at our window here. They want to know what the maximum value is in the window as we slide this window across the array. So here the maximum value is 3, and as we slide the window across, or at least when we slide it one more step, the maximum value here is 3, which is how we got 3, then 3. And when we slide it one more time, the maximum value in this window is 5, which is how they get the 5 here. And you're just going to repeat this by sliding your window across the entire array. So there's a couple ways we could do this. We could loop through the entire array, then do like a nested loop where we loop through the window and to look for our maximum value, and that would just be a 10 complexity of O of n times k, but that's the brute force way, so we're not going to do it like that. In order to do it the optimal way, you need to know what a monotonically decreasing stack is. So it's kind of like I would say that's a prereq for this problem. So I'm going to go through what that is, what a monotonically decreasing stack is. So let me just type that out, monotonically decreasing stack, so that you understand how it applies to this problem. So in a monotonically decreasing stack, as we push elements onto this stack, the elements always have to be decreasing. So let's say I push this 1. And this is just the example. So anyway, if I push this 1, it's fine. It's just like a normal stack. If I want to push this 3, well, I can't, because this is now increasing, and that breaks the whole decreasing stack property. So what we need to do first is we need to pop the 1, then push the 3. And when we want to push the -1, we just can, because it's decreasing. We go ahead and push the -3. Awesome. And when we want to push this 5, well, we can't, because then it would be increasing, right? If I push this 5, this is increasing now from -3 to 5. So what we need to do is we need to pop the -3, pop the -1, pop the 3, then push the 5. Okay, so that's how a monotonically decreasing stack works. But now how does it help us? So one attribute of a decreasing stack is that the element on the bottom is the greatest element that we've encountered so far. So let's go through that example one more time while observing that. So we push the 1. 1 is at the bottom of the stack. It is the greatest element we've encountered so far. Nice. We push, in order to push the 3, we got to pop the 1, push the 3. 3 is at the bottom of the stack. It is the greatest element that we've encountered so far. Nice. We push the -1, and this is fine because it's decreasing. And notice 3 is still at the bottom of the stack, because which means that it's the greatest element we've encountered so far. And if we push the -3, the same thing, 3 is still at the bottom of the stack. And if we push the 5, so we're going to push this guy, but we actually need to pop first. So pop the -3, pop the -1, pop the 3. And now 5 is at the bottom of the stack because it is the greatest element we've encountered so far. Now, how does that help us? Well, notice in our little sliding window problem, so let's just make a sliding window. What we're really doing here, or what we really need to know is, okay, so what's the greatest element we've encountered so far? So and actually for demonstration purposes, let me just change this to 100, and let me change this to 500. So let's just say I push all these elements into my decreasing stack. So I'm going to push 100, push the 3, push the -1. So this is just the sliding window elements. You can see that 100 is the greatest element we've encountered so far, right? And because it's at the bottom of the stack. Now, and this is decreasing. Well, when I slide my window across, let's just move our window one element over. We're going to push this -3. So let's just go ahead and push that guy. And this is still decreasing, but notice the 100 is still in there, and it's not inside of our window. It's outside the window, right? Well, all we need to do is remove the previous index so that it doesn't affect what our greatest element that we've encountered so far is. Okay, yeah. So basically, as you slide this window across, you just remove if the previous index is still in the stack, well then just remove it. And it'll be at the bottom if it is in there. So because these three elements would be on top. Okay, let me explain why it's at the bottom actually. So in this case, it was still stuck in there, right? And it's because it was the greatest element. But then, so if it wasn't the greatest element, then what would end up happening is it would have gotten kicked out. So let me just keep going, and you'll see why. So let's just say 3, -1, 3. So yeah, so this is in my stack, and now 3 is the greatest element we have so far, because we're just gonna say that we kicked the previous index out, and now the element at the bottom of the stack is 3, so that's my greatest element. And that's within my window, right? Well, now let's say I want to push this 500, so I'm going to slide this window across. And notice when I push the 500, this would be increasing, right? If I added the 500 here. So what I actually need to do is I need to pop the -3, pop the -1, then pop the 3. And notice this 3 is just going to get removed naturally if it wasn't the greatest element. And then, so after I pop the 3, then I push the 500 in. Because, if I kept the 3, this would be increasing. So I needed to get rid of this first before I could add this so that it could still be decreasing. So either way, so the previous index is just always going to be at the bottom of our stack, either because it was the greatest element, either the previous index will either be at the bottom of the stack or it won't be in the stack at all, because either it was the greatest element and it was at the bottom, or some other element kicked it out or popped it out because it broke the decreasing property. So this is actually the entire algorithm for solving this problem. As long as you know how to work with this decreasing stack, and you can handle getting rid of anything that breaks the property, and then getting rid of the index at the bottom if it's not inside of our window, then that is really the entire algorithm. So let's just code it out. So I'm going to leave this here in case I need it again for any demonstration purposes. And let's start by just declaring the stack first of all. So okay, so Java has a normal stack data structure, but we can't use a normal stack because remember so stack only has push, pop, peek, right? And we need to check the bottom of the stack. So we would need something like peek last and remove last if we want to remove the previous index that came before our window. So we're just going to use a linked list here to be able to do that. So linked list stack equals new linked list, and we need to declare our maxes array, which is, so let me just type it out. So this is just going to hold all of those maximum elements as we're sliding our window across the array. So if our window was up here, we would store 100 in maxes. Then we would store, as we slide our window, we would store 3 in maxes. So that's all the maxes array is. Okay, it's just storing those maximum elements. Okay, so let's just keep going. So what is the size of this thing? Well, the way you calculate it is, let's just say we have this. I can just show you with this guy. Let's just say I have these 3 elements, right? And this is the entire nums array. So nums.length would equal 3 here. This was my entire nums array. And let's just say that k, our window size, is still 3. Well, I need to return, maxes would equal 100. This is what I would have to, let me put some space here. This is what I would have to return, right? So that means that maxes.length is equal to 1. So what I can do here is just nums.length minus k would give us 0, because 3 minus 3 is 0. But because maxes.length is 1, we would just add 1. So nums.length minus k plus 1. Cool. So now our maxes array is the correct length, and we're going to end up returning the maxes array at the end after we do some code in the center. So now all we need to do is loop through our nums array and push it into the stack. So nums.length plus I. And remember, okay, in order to push into the stack, we have to get rid of all the elements that break our decreasing stack property. So let's just pretend we have a method that does all that for us. So we're going to call it push into or onto, right? Push to decreasing stack. Let's just call it that. Push to decreasing stack. And this would take in the stack, and this would take in nums and I. And you'll see why it does when I actually implement it. But we're just going to pretend that this is already implemented. So all this is doing is it's removing all the elements in the stack that break our decreasing property, and then it's going to finally push this index onto the stack. So this stack is going to hold the indexes of our nums array. It's not going to hold the actual values. In the examples, I did it with the values of like pushing and popping, but it's more useful to actually store the indexes of the array into the stack. And then well, anyway, let's just keep going. So we push a decreasing stack. Then what do we want to do here? We want to, okay, so we want to populate our maxes array, but we can't populate it until our whole window size is inside the stack, right? Because, okay, let's just take this example here. We're going to push, so I starts at 0. We're going to push that index into the stack. But if our window size is 3, we need to push all of these into the stack before we can check what the maximum value is at the bottom of our stack or whatever. So yeah, so we need to make sure at least the window size has been taken care of first. So let's see. So let's just make this super simple. So again, if this is the entire nums array, nums.length, or no, so so let's just say this is index 0, this is index 1, this is index 2. So we need to use I here. So if our window size would be 3. So what we actually need, since we want to start populating our maxes array when we hit this element. So like if we had 5, let's say a 12, 223, let's do a random number 100. And let's just say this was our entire nums array. We want to start populating maxes once we've gotten to this index, because now we've fulfilled our window size. So if the index here is 2 and k is 3, then what we actually need to do is I plus 1, because 2 plus 1 is 3. If it's greater or equal to k, then we can start populating our maxes array. So I hope that's clear. I know it's a little rough because I had to think through it for a second, but I think you can see why I did that. So now what do we actually put here? So we can't do I here because I would just be, so if we stick to our example, I would be 2. So we actually need to do I minus k, but this would give us -1, so we actually need to add 1. So if we just want to stick with how that looks, we could just do, let's put the +1 over here, so that looks nice. So I hope that's clear why I'm doing I have to subtract k before so I can get, so let's just say if 2 plus 1 minus our window size of 3, well, you can see that this will be 0, right? And as I increases, then this number is going to increase. So it would be 3, 4, and this will eventually be 1, 2, 3. Okay. So just wanted to make that super clear of what I'm doing. Maxes equals whatever is at the bottom of the stack. So if peak would give us what's at the top of the stack, we just want to do peak last to get us the greatest element, which would be at the bottom of the stack. Okay, so we're getting the greatest element at the bottom of the stack, but remember that this could be the previous index before our window size. So we need to remove the previous index before we actually check what the bottom element is. So we want to stack.remove last, but when do we want to do it? So if the bottom thing, so it would be peak last again. If peak last, so this would be the index equals, what are we doing here? So let's just keep doing, and let's just do another example so that we can think through it. So let's see. Let's say our window is out here. We need to remove this index here. So peak last, this would be index 0, right? And this would be index 1, then 2, then 3. But we only care about this guy. So index 0, that's what peak last would be. If it, and k is 3 in this case. So if k is 3, then what are we doing here? And then so I right now would be here. And this is index 3. So 1, 2, 3, yeah. So in this case, I equals 3. So what we can do is I minus k. Yeah. So if let's say, so the next time that I is 4, this will just be 4 minus 3, which puts us at this index of 1 to remove it on the next iteration. So, yep, let's just keep going. So we're just removing that index just before the window. If it's in there, right? We're checking first if it's there, and if it's not, then just this won't happen, or this remove last won't happen. So so we took care of the previous index. Now we now we're checking what the bottom element of our stack is for the grade, and that the element at the bottom is our greatest element within our window. And let's see, is that it? I think we're done. We just so we return maxes, the bottom here, and all we need to do is write this push to decreasing stack method, and we should be done. Oh, wait. Oh, okay, sorry, I made one little mistake here. So maxes, remember peak last, I'm storing the indexes in my stack, not the actual values. And maxes needs to hold the values, not the, so it needs to hold the value. So we just need to do nums of the index that holds our greatest element. Okay, so sorry about that. That's one little silly mistake. So now push to decreasing stack. We need to write this bad boy, and then we're done. We're done. Okay, so let's just do private void push to decreasing stack, and let's fix the arguments here, parameters, whatever. It's just a linked list, integers. We have this is an integer array, and this is the index we want to push into our decreasing stack. And now we want to just so we want to loop through. So this is where we want to remove all elements in stack that break the decreasing property. So while the stack isn't empty, and stack dot peak. Now remember, this is an index that we're going to be holding the indexes of the nums array, not the actual values. So we need to do nums. We're just accessing. So this is the index passing into nums to get the actual value inside of nums. If it's for decreasing, it's just less than or equal. So less than or equal to nums I. So if the element we're about to push into our stack, if it breaks the decreasing property, then we need to pop that element from the stack. And now we can go after. So this will take care of getting rid of all those elements, those that break the decreasing property. Now we can just push the index onto the stack. And I think we are done. Let's just go ahead and check. What did I do? Oh, okay. I have some useless comments that I didn't take out. Okay, so I just got rid of like the examples that I wrote up there, and I didn't comment them out. Cool. So run code, submit, and that is it. Now, as for time complexity, let's see. So when you're pushing onto a decreasing stack or whatever, it's just O of n. And the reason is because every element in the array that we're pushing into the stack, it's going to get pushed onto the stack one time. And it gets popped. Every element in the stack will then get popped at most once. So that just means there's at most 2 operations for every element in the array. You know, there's guaranteed one push and then possibly popping it out. So this whole thing in terms of time is just O of n. And then let's see, for space, it's just O of n because we created the stack here. And maxes actually doesn't count towards our O of n because we don't include the output. Yeah, so it's just O of n because of our stack. So that is the entire problem. And again, if you want to see more like walkthroughs and like me like kind of like showing you the prerequisites to problems and stuff like that, yeah, you can just subscribe. So later, bye.